Hi, welcome to Pre-AP Physics 5.3 on energy. Today we're going to look at potential and kinetic energy, their charts, graphs, equations, and calculations. This is focusing on mechanical energy today. So first off, what is energy? Well, the definition of energy is the capacity for doing work or producing heat. That's what energy is. The law of conservation of energy says that energy cannot be created or destroyed. It can only be transformed from one form into another. Today we're going to look at two types of energy, potential and kinetic. Both of these types of energy come from mechanical energy, but there are potential and kinetic energies for all six forms or types of energy. So first off, potential energy. Potential energy is abbreviated PE or EG. It's the energy associated with an object's height above its normal position. In a pendulum, when the pendulum is raised from position D, which is at its lowest point, to C, it has gained potential energy because it has the potential to fall. When it's raised to position A, its highest point, all the energy it has is potential because it is not moving and all it can do is fall. It has a lot of potential. Same example, the kinetic energy. Kinetic energy is associated with an object's motion. So kinetic energy depends on mass and velocity. When the pendulum moves from position A to B to C, as I let it go, it gains kinetic energy. When it reaches position D, it's moving the fastest that it will move, and all the energy is kinetic. So we're going to start by looking at the charts. A pie chart is a very good way to visualize the total amount of energy available. Position A, we said, was all potential energy because it's at its highest point. And position D was all kinetic energy because it is moving the fastest. So we would represent that by a circle pie chart that is completely marked or labeled or filled in as EG at position A. At position D, we would label it all EK because all the energy is EG at position A and all the energy is EK at position D. As it swings to its lowest point, it's moving its fastest and all the energy is converted into EK. But at positions B and C, it's got to be a mix of EG and EK. Because it's gaining speed, that means more EK, and it's losing height, that means less EG. So notice that B and C are a mixture of EG and EK, but notice two things. One, it's not perfectly even because it's never exactly in the middle between A and D. And two, notice that the EG decreases as we get closer to the bottom, and the EK increases in size of the pie chart as we get closer to the bottom. So let's transition now from a pie chart to a graph. Though pie charts are good, most of the time we will use bar graphs as if energy is represented by 4 blocks on the graph. So this is the bar graph for positions A, B, C, and D. Notice that I've only used 4 smiley faces. Also notice that the EG and the EK are the two kinds of energy that I identified. So that's what I've put in my bar graph. Okay, and I put it at every position so that I know that kind of energy is being used throughout this. Even if it is zero usage, it's still being used. So there are 4 blocks of EG at A, and then position B maybe has 3 and 1. It can't be 2 and 2 because it's not exactly in the middle. Position D then is all EK. So we did 4 blocks of EK. So if a ball is bounced, we need to be able to do the pie chart, the bar graph, and then write the equation. So here's your example, and here's some background on it. The ball has just left the ground at position A. Okay, it's being bounced. So it has just left the ground at position A. It doesn't have any height, but it is moving at its fastest. Position B is halfway to the top of the bounce. Position C is all the way at the top. Position D is halfway down, and position E is right before it hits the ground. Notice the green arrows pointing up for going up and pointing down for going down. And notice that the size of the arrow does matter. The longer the arrow, the faster it's going. So let's look at the pie charts. Position A would be all EK because, again, it doesn't have any height, and therefore it is not off the ground. It doesn't have any EG, but it is moving fast, so it does have all EK. B would be half and half EG, half EK. C would be all EG. D again would be half and half, and E would be all EK again. Translating those pie charts into bar graphs, again, position A would be all EK, 4 blocks of EK. Position B would be half and half, 2 and 2. C would be all EG. D would be half and half, and E would be all EK. Now, the energy equation is literally just the type of energy you have and its location. But notice when you have 2 different kinds of energy at the same location, the total amount of energy is the sum of those 2 different types. So the energy equation would look like this and be read. The EK at A is equal to the EK at B plus the EG at B is equal to the EG at C, which is equal to the EK at D plus the EG at D, which is equal to the EK at E. It sounds like a mouthful, but when you realize the law of conservation of energy says that energy cannot be created or destroyed, it just gets transformed from one form to another, this makes more sense. I can't create energy. It doesn't come out of nowhere. It had to come from somewhere. And here it's being transformed within mechanical energy to potential and kinetic, transformed back and forth. So let's look at calculations. In order to calculate the EG at position A, we have to know the mass, the gravity, and the height of the ball. That's what EG depends on. In order to calculate velocity, in order to calculate the EK at D, we have to know the mass and the velocity of the ball, right? Knowing the total EG or EK at any one position allows us to calculate information at other locations or other positions. So on your formula sheet, put the equation for EG. EG is equal to mgy or mgh. EG is the potential energy measured in joules. M is the mass in kilograms. G is gravity in meters per second, and Y is the height in meters. Again, be sure that you get this written down on a formula sheet and you understand that EG is mgy. Always be sure when you do any problem that your units are correct. Second box on your formula sheet, add a formula for EK. EK is 1/2 mv squared. EK is the kinetic energy, again measured in joules. M is your mass in kilograms, and V is your velocity in meters per second. Note that V squared means velocity times velocity. This is not mass times velocity and that quantity squared. It is simply mass times velocity times velocity. So let's do a problem. In our pendulum example, if A is 2 meters above the lowest point, D, and the mass of the bob is 5 kilograms, how fast is the bob moving at position D? Well, you should grab the part of the energy equation that relates A and D. So the EG at position A has to equal the EK at D. Energy is not created or destroyed. So wherever it is at one place is what it will be at the others. The energy of formula for EG is mgy, and that's at position A. That's what the parenthesis A means. And the EK at D is 1/2 mv squared at position D. Well, the mass was given as 5 kilograms. Gravity is 9.8 meters per second, and the height is 2 meters. Then the EK, 1/2, the mass, which is 5 kilograms, times the velocity squared. Solving that equation, we do get 98 is equal to 2.5 v squared. Dividing by 2.5 and taking the square root gives us a velocity of the bob at position D of 6.26 meters per second. We will be doing a lot of problems in class. Thanks for watching.